Imagine for a moment that 85% of the universe is made up of something we can't see, can't touch, and can't even fully understand. Sounds like science fiction, right? Well, welcome to the real-life mystery of dark matter and dark energy. In today's video, we're diving into 20 mind-boggling mysteries that have stumped scientists for decades and continue to spark fierce debates. From the invisible forces that hold galaxies together to the energy that might be driving the universe apart, we're breaking down the enigmas that keep astrophysicists up at night. Stick around, because by the end of this journey, you might just see the cosmos in a whole new light. So, buckle up, get ready to explore the unknown, and let's unravel the secrets of the universe together. The first mystery involves the concept of the invisible universe. Dark matter and dark energy are two of the biggest puzzles in modern astrophysics. Imagine a universe where what we can see, like stars, planets, and galaxies, makes up just a tiny fraction of the total mass. Dark matter and dark energy, though invisible, account for about 95% of the universe. Dark matter is thought to be a form of matter that doesn't emit, absorb, or reflect light, making it completely invisible to our current instruments. We know it's there because its gravitational effects can be observed in the way galaxies rotate and cluster together. Without dark matter, galaxies would fly apart. On the other hand, dark energy is even more mysterious. It's believed to be the force driving the accelerated expansion of the universe. Despite being invisible and nearly undetectable, dark energy makes up roughly 70% of the universe's total energy content. Scientists use its effects on the expansion rate of the universe to study it. The challenge with both dark matter and dark energy is that they don't interact with normal matter in ways we can easily detect, making them some of the greatest riddles in the cosmos. Understanding these invisible forces is crucial for grasping the true nature of our universe. The second mystery involves the missing mass problem. When scientists observe galaxies, they notice something peculiar. Based on the visible matter alone, galaxies don't have enough mass to generate the gravitational pull needed to hold themselves together. This means, according to the laws of physics, that galaxies should be flying apart. Yet they remain intact. Enter dark matter. Researchers propose that an invisible form of matter, dark matter, provides the extra gravitational force needed to bind galaxies together. Essentially, dark matter acts like a cosmic glue. It doesn't emit, absorb, or reflect light, making it invisible to telescopes and other instruments. But its presence can be inferred from its gravitational influence on visible matter. For example, when scientists measure the rotational speeds of galaxies, they find that stars on the outskirts are moving much faster than they should be, based on the observable mass alone. This discrepancy points to the existence of a hidden mass that exerts additional gravitational pull. Dark matter is thought to form a halo around galaxies, extending far beyond the visible edges and contributing to their overall mass. By studying the gravitational effects on galaxies, clusters of galaxies, and cosmic structures, scientists aim to map out the distribution of dark matter in the universe. Solving the missing mass problem is crucial for our understanding of galaxy formation, structure, and evolution. Without dark matter, our current models of the universe would need a major overhaul. So, while dark matter remains invisible, its gravitational fingerprint is undeniable, and it plays a fundamental role in the dynamics of cosmic structures. The third mystery involves gravitational lensing. Gravitational lensing is a phenomenon where light from a distant object, such as a galaxy or a star, is bent around a massive object like a dark matter cluster. This bending of light acts like a cosmic magnifying glass, allowing us to observe distant objects that would otherwise be too faint or obscured. What's truly fascinating is how gravitational lensing helps us indirectly see dark matter. Here's how it works. When light from a distant object passes near a massive object, the gravitational pull of that mass curves the space around it, bending the path of the light. This effect can distort the appearance of the background object, sometimes creating multiple images, rings, or arcs of the same celestial body. These distortions are a direct consequence of the gravitational field generated by dark matter. By analyzing these distortions, scientists can map out the distribution of dark matter, even though it's invisible. Think of it as using shadows to identify the shape of an unseen object. For example, when observing a cluster of galaxies, the gravitational lensing effect can reveal an elusive web of dark matter surrounding and permeating the cluster. This web influences the way light is bent and helps scientists construct a map of dark matter's layout. Furthermore, gravitational lensing has provided strong evidence supporting the existence of dark matter. Observations from the Hubble Space Telescope and other advanced instruments have shown that the amount of visible matter in galaxy clusters is insufficient to account for the lensing effects. This discrepancy indicates the presence of additional, unseen mass dark matter. Gravitational lensing not only enhances our understanding of dark matter, but also offers a powerful tool for studying the universe. By examining the way light bends around massive objects, we gain insights into the distribution and nature of dark matter, shedding light on one of the universe's most enigmatic components. The fourth mystery involves the bullet cluster. The bullet cluster is a pair of colliding galaxy clusters that provide some of the clearest evidence for the existence of dark matter and show how it behaves differently from regular matter. When these two galaxy clusters collided, something extraordinary happened. The hot gas, which accounts for most of the normal matter in the clusters, interacted and slowed down due to friction. However, the dark matter did not experience this friction and passed through the collision almost unaffected. Scientists used this cosmic event to map out dark matter and observed that while the normal matter clumped together at the center, the dark matter separated from it and spread out around the edges. This separation is key. It shows that dark matter interacts with itself and with regular matter primarily through gravity and not through electromagnetic forces, which are responsible for friction and collisions in normal matter. By studying the bullet cluster, scientists gained valuable insights into the nature of dark matter. They utilized gravitational lensing to observe the distribution of mass. The light from background galaxies was bent around the cluster, revealing areas with high concentrations of dark matter. The bullet cluster acts like a natural experiment, confirming that dark matter exists and demonstrating its unique properties. This collision has helped astrophysicists identify how dark matter behaves during such cosmic events, offering a glimpse into its elusive and unseen nature. This galactic dance not only strengthens our understanding of dark matter, but also challenges us to rethink our models of the universe. The fifth mystery involves dark energy and the accelerating universe. Imagine looking up at the night sky and realizing that not only are the galaxies drifting apart, but they're doing so at an ever-increasing pace. This baffling observation is attributed to dark energy, a mysterious force that's driving the accelerated expansion of the universe. Dark energy makes up about 70% of the universe's total energy content, yet we know very little about it. When we talk about dark energy, we're referring to a hypothetical form of energy that permeates all of space and counteracts the force of gravity. Its existence was first suggested in the late 1990s when astronomers discovered that distant supernovae were dimmer than expected, indicating that the expansion rate of the universe was speeding up. This was a groundbreaking revelation because, since the Big Bang, it was assumed that gravity would eventually slow down the expansion. However, dark energy appears to work in the opposite direction, pushing galaxies further apart at an accelerating rate. One way to visualize dark energy is by imagining a balloon being inflated. The galaxies are like spots on the surface of the balloon. As the balloon expands, the spots move away from each other. But now, imagine that the balloon isn't just expanding, it's doing so faster and faster over time. That's the effect dark energy seems to have on our universe. Scientists have proposed various theories to explain dark energy, one of which is the cosmological constant, a term introduced by Albert Einstein. The cosmological constant suggests that dark energy is a property of space itself, meaning that as the universe expands, more space is created and therefore more dark energy. This creates a repulsive force that accelerates the expansion. Another theory involves dynamic fields that change over time, similar to how magnetic fields work. While these ideas are intriguing, dark energy remains one of the biggest enigmas in cosmology. Its discovery has profound implications for the ultimate fate of the universe. If the acceleration continues indefinitely, it could lead to a scenario known as the Big Freeze, where galaxies drift so far apart that stars burn out, and the universe becomes a cold, dark, and lonely place. On the other hand, if the nature of dark energy changes, it could result in a different cosmic endgame. Understanding dark energy is crucial for comprehending the universe's past, present, and future. By observing distant celestial objects and studying the universe's expansion rate, scientists hope to unlock the secrets of this elusive force. Dark energy challenges our understanding of physics and compels us to explore the fundamental nature of reality, making it one of the most captivating mysteries in modern astrophysics. The sixth mystery involves cosmic background radiation. Cosmic microwave background radiation, or CMB, is the afterglow of the Big Bang. It's like a snapshot of the infant universe, capturing what it looked like just 380,000 years after its birth. This radiation is a vital tool for scientists studying dark matter and dark energy. The CMB is essentially a faint glow that fills the universe, detectable in every direction. It's a relic from a time when the universe was hot and dense, before stars and galaxies even existed. By examining the tiny temperature fluctuations in the CMB, scientists can uncover insights about the distribution of matter, both normal and dark matter, throughout the universe. These temperature fluctuations are minute, but they provide a wealth of information. The peaks and valleys in the CMB map are influenced by the presence of dark matter. Dark matter doesn't interact with light, but its gravitational influence affects the motion of particles in the early universe. These interactions leave subtle imprints on the CMB that we can observe today. For instance, the density of dark matter shapes how structures like galaxies formed over cosmic time. Scientists use sophisticated tools like the Planck satellite to measure these fluctuations with incredible precision. By analyzing patterns in the CMB, researchers can infer the amount and distribution of dark matter. Now, when it comes to dark energy, the CMB also plays a crucial role. The expansion rate of the universe affects the size of the temperature fluctuations we see in the CMB. Since dark energy drives the accelerated expansion of the universe, its influence can be detected in the CMB data. Essentially, by studying the CMB, scientists can trace back the history of the universe's expansion and gain clues about the properties of dark energy. The CMB is like a cosmic fingerprint, preserving information from the dawn of the universe that helps us understand the unseen forces at play. It tells a story of how the universe evolved from a hot, dense state to the vast cosmos we see today. The more we learn from the CMB, the closer we get to unraveling the mysteries of dark matter and dark energy. This ancient radiation, traveling through space for billions of years, continues to illuminate the hidden aspects of our universe, making it a key piece of the puzzle in modern astrophysics. The seventh mystery involves structure formation. To understand how dark matter helps form the large-scale structure of the universe, imagine the cosmos as a vast web of interconnected filaments and voids. This cosmic web is the scaffolding upon which galaxies, clusters, and superclusters are built. Dark matter plays a crucial role in this structure formation. In the early universe after the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, tiny fluctuations in the density of matter seeded the formation of structures. These fluctuations were imprinted in the cosmic microwave background radiation, which we discussed earlier. Dark matter, which doesn't interact with light but does exert gravitational force, began to clump together in these over-dense regions. These clumps of dark matter acted like gravitational wells, pulling in surrounding gas and dust. Over time, these clumps grew larger, merging with others to form massive halos. Inside these dark matter halos, normal matter started to cool and condense to form stars and galaxies. Think of dark matter as the invisible framework that guides the formation of visible structures. Without it, the gravitational pull would be too weak to bring together the matter needed to create galaxies. Observations and simulations show that galaxies are not randomly distributed but form patterns that resemble a cosmic web. This web-like structure is largely shaped by the distribution of dark matter. The areas with the highest density of dark matter become the nodes of this web, where clusters of galaxies are found. Between these nodes are vast empty spaces or voids with very little matter. The presence of dark matter is essential for explaining the observed large-scale structure of the universe. Computer simulations, like those run by the Millennium Simulation Project, show that when dark matter is included in the models, the resulting structures closely match what we see in the universe. These simulations start with the conditions of the early universe and let it evolve over billions of years, revealing how dark matter's gravitational influence shapes the cosmos. By studying the distribution and behavior of dark matter, scientists can gain insights into the processes that drive galaxy formation and evolution. Understanding how dark matter contributes to structure formation not only helps us comprehend the current arrangement of the universe, but also provides clues about its past and future. This mysterious substance, though invisible, is a fundamental component in the cosmic dance that creates the vast and intricate structures we observe in the universe today. So, as we continue to explore the mysteries of dark matter, we're also uncovering the secrets of how the universe came to be and how it continues to evolve. The eighth mystery involves the cosmic web. Imagine the universe as a massive, intricate tapestry woven with threads of dark matter. This cosmic web is the large-scale structure of the universe, connecting galaxies and clusters in a vast, interconnected network. Dark matter plays a pivotal role in knitting this web together. In the early universe, regions with slightly higher densities of matter began to attract more matter through their gravitational pull. Dark matter, which does not emit or absorb light, formed the backbone of these dense regions. Over billions of years, these regions grew and merged, creating the fibrous structure known as the cosmic web. The cosmic web consists of filaments, nodes, and voids. Filaments are the dense strands of dark matter that connect galaxy clusters, forming the bridges between nodes. Nodes are the points where filaments intersect, often containing the largest clusters of galaxies. Voids are the vast, empty spaces between filaments containing very little matter. Dark matter's gravitational influence is fundamental in shaping these structures. By acting as a scaffolding, dark matter provides the framework for visible matter to accumulate and form galaxies. Computer simulations of the universe, which incorporate dark matter, reveal the intricate patterns of the cosmic web. These simulations show that the distribution of galaxies follows the underlying dark matter structure. Observations from telescopes like the Sloan Digital Sky Survey have mapped the positions of millions of galaxies, confirming the existence of this web-like arrangement. The cosmic web is not static, it evolves over time. As dark matter continues to clump together, it draws more matter into its gravitational wells, causing the web to grow and change. This dynamic process influences the formation and evolution of galaxies, clusters, and even the overall expansion of the universe. Understanding the cosmic web provides valuable insights into the role of dark matter in the universe. By studying the large-scale structure, scientists can infer the properties of dark matter and its distribution. It's like tracing the threads of an invisible fabric to understand how the universe is stitched together. As we continue to unravel the mysteries of the cosmic web, we gain a deeper understanding of the fundamental forces and processes that shape our universe. This vast, interconnected network is a testament to the power of dark matter in sculpting the cosmos, revealing the hidden beauty and complexity of the universe's large-scale structure. The ninth mystery involves dark matter detection efforts. Over the years, scientists have devised various ingenious experiments to directly detect dark matter. One approach involves the use of underground laboratories. These labs are located deep beneath the Earth's surface to shield sensitive detectors from background radiation and cosmic rays. One such experiment is the Large Underground Xenon or LUX detector. It uses liquid xenon to try and capture dark matter particles known as WIMP, or weakly interacting massive particles. When a WIMP collides with a xenon nucleus, it generates a tiny flash of light, which can then be detected by sensors surrounding the tank. Another promising experiment is the Cryogenic Dark Matter Search, or CDMS. This experiment uses supercooled germanium and silicon crystals to detect the heat and ionization produced when a dark matter particle interacts with an atomic nucleus. The extreme cold reduces thermal noise, making it easier to spot these rare interactions. Scientists are also exploring space-based detectors. The Alpha Magnetic Spectrometer, or AMS, aboard the International Space Station is one such example. It measures cosmic rays and looks for anomalies that might signal the presence of dark matter particles. The AMS can detect positrons and antiprotons, which could be produced when dark matter particles annihilate each other. Particle accelerators like the Large Hadron Collider, or LHC, are also in the hunt for dark matter. By smashing protons together at nearly the speed of light, the LHC creates conditions similar to those just after the Big Bang. Researchers hope that these high-energy collisions might produce dark matter particles that can be detected indirectly by observing missing energy and momentum in the aftermath of the collisions. Additionally, scientists are utilizing gravitational wave observatories like LIGO and Virgo to search for dark matter. These observatories can detect ripples in space-time caused by massive objects such as black holes merging. Some theories suggest that dark matter could form compact objects that, when they collide, might produce detectable gravitational waves. Despite these innovative and varied approaches, detecting dark matter has proven to be an elusive challenge. Each experiment brings us a step closer to unlocking this cosmic mystery. By combining the results from underground, space-based, and collider experiments, scientists hope to identify the nature of dark matter particles and understand their properties. It's a global effort involving researchers from around the world, all working towards one common goal: to reveal the unseen substance that shapes our universe. The pursuit of dark matter detection not only pushes the boundaries of technology and science, but also deepens our understanding of the fundamental components that make up the cosmos. As we continue these efforts, we inch closer to demystifying dark matter and uncovering the secrets it holds. The 10th mystery involves WIMP and actions. These are two of the leading candidates thought to make up dark matter. Let's demystify what each of these particles is and why they are so important in our quest to understand the universe. Starting with WIMP, or weakly interacting massive particles, these are hypothetical particles that have mass and only interact through gravity and the weak nuclear force. Unlike particles of normal matter that interact through the strong nuclear force and electromagnetism, WIMP barely interact with anything, making them incredibly difficult to detect. Scientists believe WIMP could be a major component of dark matter because they fit well into particle physics standard model extensions such as supersymmetry. The idea is that in the early universe, WIMP were created in large quantities during the Big Bang. While most of them would have annihilated each other, a small fraction would have persisted, permeating throughout the universe today. Their gravitational effects could account for the unseen mass we attribute to dark matter. Researchers are conducting experiments with highly sensitive detectors in underground labs, using sophisticated technologies to capture the rare interactions between WIMP and normal matter. These experiments aim to observe the telltale flash or heat from a WIMP colliding with a nucleus, providing direct evidence of their existence. On the other hand, actions are another dark matter candidate, but they differ significantly from WIMP. Actions are ultra-light particles proposed to solve a problem in quantum chromodynamics, the theory that describes the strong nuclear force. These particles are predicted to have an exceptionally small mass, yet an abundance of them could contribute significantly to the dark matter in the universe. Unlike WIMP, actions do not arise from the need to expand the standard model, but rather offer a solution to a theoretical puzzle within it. Actions are thought to interact with electromagnetic fields under certain conditions, which opens up a different approach to detection. Scientists are designing experiments using resonant cavities and strong magnetic fields to try and convert actions into detectable photons. This process involves tuning these detectors to specific frequencies where actions are expected to produce a signal. The Action Dark Matter Experiment, or ADMX, is at the forefront of these searches, using highly sensitive microwave resonators to hunt for those elusive action signals. Both WIMP and actions represent two very different but compelling possibilities in our understanding of dark matter. They guide current research and drive the development of advanced detection technologies. As scientists continue to refine their experiments and explore these candidates, each step brings us closer to the possible discovery of dark matter particles. Whether it's the heavy, weakly interacting WIMP or the ultra-light, elusive actions, cracking this mystery could revolutionize our understanding of the universe's composition and fundamental forces. The 11th mystery involves modified gravity theories. While dark matter is the most widely accepted explanation for the missing mass in the universe, some scientists propose an entirely different approach, modifying our understanding of gravity itself. These modified gravity theories suggest that the laws of gravity as described by Newton and Einstein might not be complete, especially on cosmic scales. One of the prominent theories is modified Newtonian dynamics, or MUND, proposed by Israeli physicist Mordechai Milgrom in the 1980s. MUND suggests that Newton's laws break down at extremely low accelerations, which are common in the outer regions of galaxies. Instead of invoking dark matter to account for the observed gravitational effects, MUND proposes that gravity itself behaves differently in these regimes. In MUND, the force of gravity transitions from the familiar inverse square law to a different relationship at low accelerations. This adjustment can explain the flat rotation curves of galaxies, where stars far from the center move at unexpectedly high speeds without the need for dark matter. Critics argue that while MUND can describe the behavior of individual galaxies, it struggles to account for the dynamics of galaxy clusters and the large-scale structure of the universe. Another approach is TVS, or tensor vector scalar gravity, developed by physicist Jacob Bekenstein as a relativistic extension of MUND. TVS incorporates additional fields into Einstein's theory of general relativity. This modification aims to preserve the successful aspects of MUND while extending its applicability to larger scales and stronger gravitational fields. TVS introduces new fields that interact with matter and spacetime, potentially offering explanations for phenomena attributed to dark matter. These theories are part of a broader class known as modified gravity, or MOG. They challenge the dark matter paradigm by tweaking the fundamental laws of gravity to account for the observed discrepancies. For example, another theory, FR gravity, modifies the equations of general relativity by altering the function that describes the curvature of spacetime. These modifications can lead to different predictions about the behavior of galaxies and the expansion of the universe without invoking dark matter. While modified gravity theories offer intriguing alternatives, they face significant challenges. Observations from the cosmic microwave background radiation, gravitational lensing, and galaxy cluster dynamics provide strong evidence for the existence of dark matter. These phenomena are well explained by the dark matter model, but require complex adjustments in modified gravity theories. Nonetheless, exploring these alternative theories pushes the boundaries of our understanding and encourages us to question the fundamental laws of physics. Modified gravity theories highlight the importance of continually testing and refining our models of the universe. They remind us that science is a dynamic process driven by curiosity and the quest for deeper understanding. Whether the ultimate answer lies in dark matter, modified gravity, or a combination of both, these investigations bring us closer to unraveling the mysteries of the cosmos. The 12th mystery involves dark energy and vacuum energy. Imagine the vast emptiness of space. Even in the vacuum of space devoid of matter, there exists a form of energy known as vacuum energy. This concept stems from quantum field theory, which suggests that even in the lowest energy state or vacuum state, quantum fields still exhibit fluctuations. These fluctuations are not empty but consist of transient virtual particles that pop in and out of existence. Vacuum energy is essentially the energy intrinsic to these quantum fluctuations. Now, this is where it gets intriguing. Dark energy, the mysterious force driving the accelerated expansion of the universe, might be closely related to this vacuum energy. One of the leading theories proposes that dark energy is a manifestation of vacuum energy, permeating all of space and contributing to the accelerated expansion. In this scenario, the energy density of the vacuum exerts a repulsive force, counteracting gravity and causing galaxies to move away from each other at an ever-increasing rate. The concept of vacuum energy is not new. It traces back to Einstein's cosmological constant, a term he introduced in his equations of general relativity to achieve a static universe. Although Einstein later discarded it, calling it his greatest blunder, the discovery of the universe's accelerated expansion revived interest in the cosmological constant as a potential explanation for dark energy. The cosmological constant represents a fixed energy density filling space uniformly, akin to the property of vacuum energy. However, significant challenges remain in reconciling the theoretical predictions of vacuum energy with observations. The value predicted by quantum field theory for vacuum energy density is vastly larger than what we observe as dark energy. This discrepancy, known as the cosmological constant problem, remains one of the biggest puzzles in modern physics. Some theories suggest that new physics or mechanisms we have yet to discover might explain this enormous difference. Understanding the relationship between dark energy and vacuum energy is crucial for resolving this enigma. Researchers are exploring various approaches, including string theory and extra dimensions, to find a more comprehensive explanation. Observationally, scientists study the effects of dark energy on the expansion of the universe through measurements of distant supernova, the cosmic microwave background, and large-scale cosmic structures. Each of these cosmic clues helps refine our understanding of dark energy and its possible connection to vacuum energy. By improving the precision of these observations, scientists hope to uncover the true nature of dark energy and its relationship to vacuum energy. As we delve deeper into this mystery, we edge closer to unlocking the secrets of one of the most perplexing phenomena in the universe. The interplay between dark energy and vacuum energy not only challenges our understanding of fundamental physics, but also reshapes our view of the cosmos, highlighting the unseen forces that govern its fate. The 13th mystery involves quantum fluctuations. Imagine taking a closer look at what we consider to be empty space. On a very tiny scale, this emptiness is far from void. Quantum fluctuations are tiny, temporary changes in energy that occur spontaneously even in the vacuum of space. These minute fluctuations are a fundamental aspect of quantum theory, where particles and antiparticles constantly pop in and out of existence, momentarily disturbing the vacuum state. Now, this gets even more fascinating when we think about dark energy. Some scientists propose that the mysterious dark energy driving the accelerated expansion of the universe might be closely linked to these quantum fluctuations. Essentially, the energy from these fluctuations could contribute to the overall energy density of space, producing a repulsive force that pushes galaxies apart. In the framework of quantum field theory, every point in space has a certain amount of vacuum energy due to these fluctuations. While the individual effects of these quantum events are incredibly small, their collective influence on a grand scale could be immense. This concept aligns with the idea of vacuum energy, which we discussed earlier. However, there's a substantial challenge known as the cosmological constant problem. The amount of vacuum energy predicted by quantum field theory is significantly greater than what we observe as dark energy. This enormous discrepancy has puzzled scientists for decades. Some suggest that new physics or unknown mechanisms might be at play, helping to balance these scales. Researchers are exploring various theories, such as the interplay between quantum mechanics and general relativity, to better understand this connection. Observational tools like the Hubble Space Telescope and the upcoming James Webb Space Telescope aim to gather more data on cosmic expansion, offering clues about the underlying nature of dark energy and quantum fluctuations. By probing the universe at both the largest and the smallest scales, scientists hope to bridge the gap between quantum fluctuations and dark energy. These investigations are crucial for unraveling the mysteries of our cosmos, challenging us to rethink our understanding of the fundamental forces that shape our universe. As we deepen our exploration of quantum fluctuations, we may uncover new insights that could revolutionize our comprehension of dark energy and the very fabric of space itself. The 14th mystery involves the fate of the universe. When we think about the ultimate destiny of the cosmos, dark energy plays a central role in determining what lies ahead. Based on our current understanding, dark energy, the mysterious force driving the accelerated expansion of the universe, will shape its fate in profound ways. Imagine the universe as a giant balloon that is constantly inflating. Dark energy is like an invisible force causing this balloon to expand faster and faster. But what does this mean for the future? There are a few possible scenarios that scientists consider. The first scenario is known as the Big Freeze or heat death. In this scenario, the universe continues to expand at an accelerating rate due to the influence of dark energy. Over time, galaxies will drift further and further apart, eventually becoming isolated from one another. Stars will burn out and new stars will no longer form. The cosmos will grow cold and dark as the remnants of stars, black holes, and other celestial objects slowly decay. This leads to a state of maximum entropy, where the universe reaches thermal equilibrium and no significant energy exchanges occur. Essentially, the universe becomes a vast, dark, and lifeless expanse. Another potential fate is the Big Rip. If dark energy's influence increases over time, it could lead to a scenario where the expansion rate becomes so extreme that it eventually tears apart galaxies, stars, planets, and even atomic structures. This catastrophic end would result in the universe being ripped apart at every level, culminating in a singularity where space and time cease to exist as we know them. This dramatic possibility depends on the nature of dark energy and whether its effects grow stronger over time. A third scenario is the Big Crunch. Although it seems less likely given current observations, if dark energy were to somehow reverse and become attractive rather than repulsive, the expansion of the universe could halt and reverse. In this case, gravity would eventually pull galaxies back together, causing the universe to collapse in on itself. This rapid contraction could lead to a massive implosion, culminating in a singularity similar to the one believed to have initiated the Big Bang. This cyclical model suggests that the universe could undergo endless cycles of expansion and contraction. Lastly, there's the possibility of a big bounce. This speculative scenario combines elements of the Big Crunch and the Big Bang, proposing that the universe's collapse could lead to a new expansion phase, essentially bouncing back and restarting the cycle of cosmic evolution. While these ideas are fascinating, they highlight how much we still don't know about dark energy. To better understand the universe's fate, scientists are conducting observations to measure the expansion rate more precisely. By studying distant supernova, the cosmic microwave background, and the distribution of galaxies, researchers hope to uncover the true nature of dark energy. These observations will help us refine our models and theories about the universe's ultimate destiny. The fate of the universe is a profound question that touches on the deepest aspects of cosmology and fundamental physics. Whether it's a frozen, dark expanse, a cosmic tear, a dramatic collapse, or a rebirth, dark energy holds the key to unlocking the ultimate fate of the cosmos. As we continue to explore and understand this mysterious force, we edge closer to unraveling one of the greatest mysteries of all time. The 15th mystery involves the cosmological constant. Albert Einstein once called it his biggest blunder, but today it's a cornerstone in the study of dark energy and the accelerating universe. To understand its significance, let's travel back to the early 20th century. When Einstein formulated his theory of general relativity, he realized that gravity would cause a static universe to eventually collapse. To counteract this, he introduced the cosmological constant, a term in his equations that added a repulsive force to balance gravity and achieve a stable universe. However, when Edwin Hubble discovered that the universe is actually expanding, Einstein abandoned the cosmological constant, considering it a mistake. Fast forward to the late 1990s, astronomers observing distant supernova found that the universe's expansion is accelerating, not slowing down. This unexpected discovery brought the cosmological constant back into the spotlight. What Einstein had once discarded became a crucial element in explaining dark energy, the mysterious force driving this accelerated expansion. The cosmological constant is now understood as a property of space itself, representing a constant energy density that fills the vacuum of space. It acts as a repulsive force, counteracting gravity and pushing galaxies apart. This aligns with the idea of vacuum energy in quantum field theory, where even empty space has energy due to quantum fluctuations. The magnitude of this repulsive force directly affects the expansion rate of the universe. The concept of the cosmological constant helps explain why galaxies are drifting apart faster and faster. Despite its importance, there's still a significant puzzle known as the cosmological constant problem. Quantum field theory predicts a vacuum energy density that's vastly larger than what we observe as dark energy. This enormous discrepancy suggests that either our understanding of vacuum energy is incomplete or new physics is at play. Researchers are exploring various theories to resolve this issue, including modifications to general relativity or new fields and particles. By studying the universe's expansion through observations of the cosmic microwave background, galaxy distributions, and supernova, scientists aim to refine the value of the cosmological constant and uncover the true nature of dark energy. Einstein's biggest blunder has evolved into a profound mystery that challenges our understanding of the cosmos. This journey from mistake to central concept highlights the dynamic nature of scientific discovery, where even discarded ideas can hold the key to understanding the universe's most enigmatic forces. The cosmological constant continues to intrigue and inspire, driving us to explore the fundamental nature of reality and the fate of the universe. The 16th mystery involves dark matter halos. When we observe galaxies, we're not just seeing the stars, gas, and dust that make them up. Surrounding these galaxies are vast, invisible halos of dark matter, which are crucial to our understanding of cosmic structures. Dark matter halos are like the scaffolding that supports the visible components of galaxies. Although we can't see dark matter directly, its presence is inferred through its gravitational effects. These halos extend far beyond the visible edges of galaxies, often encompassing a region much larger than the galaxy itself. Imagine a galaxy like the Milky Way. If you could view it with dark matter highlighted, you'd see a massive spherical halo of dark matter enveloping the spiral of stars and gas. This halo is what allows galaxies to maintain their structure and rotation speeds. Without the extra gravitational pull from dark matter, outer stars in galaxies would not orbit at the high speeds they do. They would drift away into space. The concept of dark matter halos is critical for explaining the flat rotation curves of galaxies. When scientists measure the rotation speeds of stars far from the galactic center, they find these speeds remain constant or flat, rather than decreasing as expected with only visible mass. This implies the presence of additional, unseen mass dark matter. These halos also play a vital role in galaxy formation and evolution. In the early universe, regions of higher dark matter density acted as seeds for the formation of galaxies. Dark matter's gravity pulled in normal matter, leading to the creation of stars and galaxies within these halos. Over time, these structures grew and merged, forming the complex cosmic web we observe today. The distribution and density of dark matter halos influence the clustering of galaxies, affecting everything from the formation of galaxy clusters to the behavior of gravitational lensing. Observing how light from distant objects bends around galaxy clusters helps map the distribution of dark matter, revealing the structure of these halos. Advanced simulations, such as the Millennium simulation, incorporate dark matter halos to replicate the large-scale structure of the universe. These simulations match observations incredibly well, reinforcing the idea that dark matter is a fundamental component of cosmic structure. By studying dark matter halos, scientists hope to uncover more about the nature of dark matter itself. Questions remain about its composition, how it interacts with normal matter, and its role in the universe's evolution. The vast, unseen halos of dark matter surrounding galaxies are a testament to the mysterious nature of our cosmos, guiding researchers in their quest to understand the invisible forces that shape our universe. The 17th mystery involves macho, or massive compact halo objects. When we think about dark matter, one intriguing possibility is that it could be made up of macho. These are objects like black holes, neutron stars, white dwarfs, and other compact stellar remnants that might be lurking in the halos of galaxies. Unlike particles like WIMP or actions, macho are macroscopic objects that could account for a portion of the unseen mass we attribute to dark matter. The idea behind macho is that they are ordinary matter, but in forms that are difficult to detect because they emit little to no light. For instance, consider black holes. They have immense gravitational pull but are nearly invisible because they don't emit light. Similarly, neutron stars and white dwarfs, while not as extreme as black holes, are faint and hard to detect against the backdrop of space. If a significant number of these objects exist in the outskirts of galaxies, they could contribute to the additional gravitational forces observed. One method of detecting macho is through gravitational microlensing. This phenomenon occurs when a macho passes in front of a distant star, its gravitational field bending the light from that star and causing it to temporarily brighten. This lensing effect can be observed and measured, offering clues about the presence and mass of these hidden objects. Projects like the Optical Gravitational Lensing Experiment, or OGLE, have been scanning the skies for these microlensing events to identify macho. While studies have detected numerous microlensing events, the findings suggest that macho alone cannot account for all the dark matter in the universe. They might represent a portion of it, but other forms like WIMP or actions likely still play a significant role. The search for macho continues to be a fascinating aspect of dark matter research. By studying these massive compact objects, scientists hope to piece together more of the puzzle surrounding the unseen mass in the universe. Whether macho make up a small or substantial part of dark matter, their study deepens our understanding of the hidden components of the cosmos and the complex gravitational forces at play. As we continue to observe and explore the universe, macho remain a compelling piece of the dark matter mystery, highlighting the diverse possibilities that could explain the unseen mass shaping our galaxies. The 18th mystery involves galaxy rotation curves. When astronomers measure the rotation speeds of stars and gas in galaxies, they encounter something peculiar. According to the laws of gravity, we would expect the stars at the outer edges of a galaxy to rotate more slowly than those near the center, where most of the visible mass, like stars and gas, is concentrated. However, observations show that stars on the outskirts of galaxies rotate at roughly the same speed as those closer to the center. This phenomenon is known as the flat rotation curves of galaxies, and it strongly suggests the presence of dark matter. Imagine a figure skater spinning with their arms outstretched. When the skater pulls their arms in, they spin faster because the mass is concentrated closer to their center. Similarly, in a galaxy, if all the mass were concentrated at the center, the outer stars should orbit more slowly. Yet, the flat rotation curves indicate that there is additional, unseen mass extending far beyond the visible edges of galaxies. This unseen mass is what we call dark matter. To explain these flat rotation curves, scientists propose that galaxies are embedded in massive halos of dark matter. These halos provide the extra gravitational pull needed to keep the outer stars moving at high speeds. The concept of dark matter halos aligns with other observations, such as gravitational lensing and the large-scale structure of the universe. By studying the rotation curves of different galaxies, researchers can infer the distribution and density of dark matter within them. This helps construct detailed models of dark matter halos and understand how they interact with visible matter. Advanced simulations, like those from the Millennium Simulation Project, incorporate dark matter to replicate the observed rotation curves and structure of galaxies. These simulations closely match the actual observations, reinforcing the role of dark matter in shaping galaxies. The flat rotation curves not only provide compelling evidence for dark matter, but also challenge our understanding of gravity and cosmic dynamics. By continuing to measure and analyze galaxy rotation curves, scientists aim to uncover more about the nature and distribution of dark matter, bringing us closer to solving one of the universe's most intriguing mysteries. This ongoing research into galaxy rotation curves is crucial for unraveling the secrets of dark matter and understanding the hidden forces that govern the cosmos. The 19th mystery involves dark matter in the Milky Way. As we peer into our own galaxy, the Milky Way, we encounter compelling evidence that points to the presence of dark matter right in our cosmic backyard. The rotational speeds of stars and gas in the Milky Way offer a tantalizing clue. When astronomers measure these speeds, they observe that stars on the outer edges of the galaxy move much faster than would be expected if only the visible matter were present. This discrepancy suggests that an unseen mass, dark matter, is providing the additional gravitational pull necessary to keep these stars in their high-speed orbits. This unseen mass forms a halo around our galaxy, extending far beyond the visible spiral arms. The presence of dark matter in the Milky Way is also inferred from observations of the galaxy's structure and dynamics. The distribution of stars and the way they form various patterns and clusters speak to an underlying scaffold of dark matter. When scientists map out the mass distribution in the Milky Way, they find that the visible matter alone cannot account for the galaxy's observed gravitational effects. The extra mass attributed to dark matter helps explain the stability and shape of the Milky Way's disk. Gravitational lensing, although observed more prominently on a cosmic scale, also provides evidence for dark matter within our galaxy. The way light from distant stars bends as it passes through the Milky Way's gravitational field suggests the presence of a substantial amount of invisible matter. This effect, while subtle within our galaxy, aligns with the patterns observed in other galaxies and galaxy clusters, reinforcing the case for dark matter. Researchers also study the motion of satellite galaxies and globular clusters orbiting the Milky Way. These smaller celestial bodies are influenced by the Milky Way's gravitational field, which is heavily dominated by dark matter. By analyzing their orbits, scientists can estimate the distribution and density of dark matter in and around the Milky Way. Additionally, the search for dark matter particles is not limited to distant galaxies. Experiments located deep underground and aboard space-based platforms are designed to detect potential dark matter interactions here on Earth. These experiments aim to capture the rare events when dark matter particles might interact with normal matter, providing direct evidence of their presence. Understanding dark matter in the Milky Way is crucial for grasping the overall dynamics of our galaxy. It not only influences the motion of stars and the stability of galactic structures, but also plays a fundamental role in the Milky Way's formation and evolution. As we continue to map and study our galaxy, the evidence for dark matter becomes increasingly compelling, painting a portrait of a universe shaped by forces largely unseen yet profoundly influential. By uncovering the mysteries of dark matter within the Milky Way, we gain insights into the very fabric of our cosmic home and the fundamental nature of the universe itself. The 20th mystery involves the Big Bang and dark energy. To grasp the connection between the rapid expansion following the Big Bang and dark energy, we need to travel back to the universe's infancy. The Big Bang theory describes how the universe began as an incredibly hot and dense point approximately 13.8 billion years ago. In a fraction of a second after the Big Bang, the universe underwent a period of exponential expansion known as inflation. During this phase, space itself expanded faster than the speed of light, smoothing out any initial irregularities and setting the stage for the formation of galaxies and large-scale structures. This rapid expansion was driven by a high-energy field, and when inflation ended, the energy from this field was transferred to particles, giving rise to the hot, dense state that eventually evolved into the universe we observe today. Now, let's connect this to dark energy. While inflation was a short-lived burst of rapid expansion in the early universe, dark energy is the mysterious force causing the current accelerated expansion of the universe. Although they operate on different timescales and under different conditions, both inflation and dark energy involve the concept of a repulsive force driving the expansion of space. If we think of inflation as the universe's initial growth spurt, dark energy is like a second wind, pushing galaxies apart at an accelerating rate. This accelerated expansion, first discovered in the late 1990s through observations of distant supernova, was unexpected because it was thought that gravity would gradually slow down the expansion over time. Instead, dark energy has been causing the expansion to speed up. One theory to explain this involves the cosmological constant, which Albert Einstein originally introduced as a term in his equations of general relativity. The cosmological constant can be interpreted as a form of vacuum energy, an intrinsic energy present even in empty space. This aligns with the idea that dark energy is a property of space itself, exerting a constant repulsive force. Another theory proposes that dark energy could be a dynamic field, similar to the one that drove inflation, but with different properties and effects on the universe's expansion. By studying the current accelerated expansion, scientists hope to uncover clues about the nature of dark energy and its potential connection to the early universe's inflationary period. The challenge is to reconcile these two phases of rapid expansion within a unified framework that can describe the entire history of the universe. Observations of the cosmic microwave background radiation, large-scale galaxy surveys, and precise measurements of the universe's expansion rate all contribute to this quest. They provide critical data that helps refine our models and theories, bringing us closer to understanding how the universe evolved from its explosive birth to its current accelerating expansion. The link between the Big Bang and dark energy remains one of the most profound mysteries in cosmology. As researchers delve deeper into this connection, they not only seek to explain the past but also to predict the future of our ever-expanding universe. Understanding this relationship could unlock the secrets of the universe's origin, structure, and ultimate fate, shedding light on the hidden forces that continue to shape the cosmos. The 21st mystery involves interactions of dark matter. Now, let's consider whether dark matter particles interact with each other or with regular matter. Unlike normal matter, dark matter does not emit, absorb, or reflect light, making it invisible to our current observational tools. This invisibility suggests that if dark matter particles interact with each other or with normal matter, they do so weakly, primarily through gravity. Gravity is the only force known to act on dark matter, which is why we observe its effects on the rotation curves of galaxies, gravitational lensing, and the large-scale structure of the universe. However, the lack of electromagnetic interaction makes direct detection challenging. Scientists use highly sensitive detectors deep underground to capture rare potential interactions between dark matter particles and atomic nuclei. These experiments aim to observe the tiny flashes or heat produced when dark matter particles, such as WIMP, collide with normal matter. Despite numerous attempts, no unequivocal detections have yet been confirmed, adding to the enigma of dark matter's elusive nature. The idea of dark matter interacting with itself is equally intriguing. The bullet cluster provides a fascinating case where normal matter and dark matter behaved differently during a collision of galaxy clusters. The normal matter, in the form of hot gas, slowed down due to friction, while dark matter passed through unaffected, suggesting minimal or no interaction among dark matter particles themselves. This observation supports the notion that dark matter primarily interacts through gravity. Theoretical physicists continue to explore various models to explain dark matter interactions. One such model involves hypothetical particles called actions, which could interact with electromagnetic fields under specific conditions, potentially allowing for indirect detection through their conversion to photons. The search for actions and other dark matter candidates continues to drive innovative experiments and technologies. Understanding the interactions of dark matter is crucial for unveiling its true nature and role in the universe. It challenges our understanding of particle physics and cosmology, pushing us towards new frontiers in science. As research progresses, we move closer to deciphering the mystery of dark matter interactions, potentially revealing profound insights about the hidden components of our cosmos. The 22nd mystery involves the role of supercomputers. When it comes to understanding dark matter and dark energy, supercomputers are essential tools that help scientists simulate the complex behaviors of these elusive forces. Imagine trying to recreate the entire history of the universe from the Big Bang to the present day within a computer. This is where supercomputers come in. They perform calculations at incredibly high speeds, allowing researchers to create detailed models of cosmic phenomena. One of the main benefits of these simulations is their ability to incorporate vast amounts of data from observations. Scientists input information about the distribution of galaxies, the cosmic microwave background, and the behavior of large-scale structures. With this data, supercomputers can simulate the gravitational effects of dark matter and the accelerated expansion caused by dark energy. These simulations reveal how dark matter clumps together to form the scaffolding for galaxies, and how dark energy influences the universe's expansion rate. For instance, the Millennium simulation is one of the most famous projects that used supercomputers to model the universe. It demonstrated how dark matter forms a cosmic web, with galaxies clustering along filaments of dark matter. By comparing the simulation's outcomes with actual astronomical observations, scientists can test their theories and refine their models. This process is vital for understanding the properties and distribution of dark matter. Similarly, simulations help explore different scenarios for dark energy. By tweaking variables and assumptions, researchers can see how different types of dark energy would affect the universe's expansion. This helps them identify which models best match the observed data. Supercomputers also enable scientists to study phenomena that are difficult to observe directly, such as the behavior of dark matter during galaxy collisions or the influence of dark energy on the formation of cosmic structures. By replicating these events in a virtual environment, researchers gain insights that would be impossible to obtain otherwise. The use of advanced algorithms and machine learning techniques further enhances the capabilities of supercomputers. These tools analyze vast datasets, identify patterns, and make predictions about the behavior of dark matter and dark energy. This combination of computational power and sophisticated algorithms accelerates the pace of discovery, pushing the boundaries of what we know about the universe. In summary, supercomputers play a crucial role in unraveling the mysteries of dark matter and dark energy. They allow scientists to create detailed simulations, test hypotheses, and refine their understanding of these fundamental components of the cosmos. As technology advances and computational power increases, the insights gained from supercomputer simulations will continue to illuminate the hidden forces shaping our universe. In summary, we've journeyed through the captivating world of dark matter and dark energy, uncovering mysteries that challenge our understanding of the universe. From the invisible forces holding galaxies together to the cosmic web weaving the fabric of the cosmos, each mystery brings us closer to comprehending the vast, unseen components of our reality. The enigmatic nature of dark matter, with its gravitational fingerprints, and the puzzling effects of dark energy driving the accelerated expansion of the universe, continue to spark intense research and debate. The quest to detect dark matter particles, explore modified gravity theories, and understand the interplay of vacuum energy and quantum fluctuations highlights the dynamic and evolving nature of scientific discovery. The role of advanced simulations and supercomputers has been pivotal in modeling these phenomena, offering profound insights into the hidden forces shaping our universe. As we probe deeper into these cosmic enigmas, we unravel the threads of an ever-expanding story that redefines our place in the cosmos. The excitement of ongoing research and the possibility of revolutionary discoveries remind us that the universe is full of wonders yet to be explored. So stay curious, keep questioning, and join us in this incredible voyage to unlock the secrets of the universe. Don't forget to like this video, subscribe to our channel, and hit the notification bell to stay updated on the latest cosmic discoveries. Your journey through the cosmos has only just begun.